So, welcome all of you. Now, we started discussing heteronuclear NMR spectra since last class. Of course, we discussed extensively carbon 13. In the last class, I showed you how we can utilize depth, an experiment in carbon 13. 3 different type of experiments you can do with the last flip angle of the proton as 45 degree, 90 degree and 135 degree. Based on that, we can identify the different carbons attached to different number of protons. And I also showed you how we can utilize this depth experiment in identify the correct structure of some small molecules like monoterpenes. 2 such examples we saw. Extending further, we started analyzing the spectrum of other nuclei. We took the example of fluorine NMR. Fluorine is 100% abundant, spin-off nuclei, very friendly nuclei. We started doing that. And we analyzed spectra of many of the molecules. Couple of examples I took. How we can see fluorine coupling, fluorine proton coupling, and how the multiplicity pattern arises, we understood. And analyzed simple example, couple of molecules. And we also analyzed molecule where some other dilute spin can appear and give rise to satellite like in proton spectrum. So, we took the example of mercury containing molecule, where mercury coupling to fluorine appear as satellites on either side. Separation of that, if you measure, you will get mercury fluorine coupling. This is what happened. So, afterwards, another interesting observation I wanted to tell you was the fluorine is very sensitive to isotopic substitution. We took the example of simple molecule difluorobromomethane, where just substitution of bromine 79 and 81 gives us a small change in the chemical sheet position, because there will be 4 different types of isotopomers in that molecule corresponding to bromine both in 79, both in 81 and 179 other 81 with 2 such possibilities. We got the statistical distribution of population gives different intensity peaks. Same thing we observed for CFCl3. CFCl3 is a simple molecule. Fluorine NMR should give you a single peak, but it gives 4 peaks of intensity 100, 95, 30 and 3. And this we could explain the intensity pattern based on the statistical distribution of the population of different isotopomers of molecule containing different chlorine. Chlorine 35 and chlorine 37 is there. Chlorine 35 76% abundant, chlorine 37 24% abundant. Find out all the possible different isotopomers present, and then we could get the information and number of populations of each of the isotopomers, and statistical distribution of that gives different chemical shifts, and we were able to get all the peaks we could assign and also the intensity pattern. Continuing further, today we look at the isotopic effect because of deuterium, and another example and a deuterated molecule called vinyl fluoride. We look at this molecule now. For example, in the vinyl fluoride, if we take only fluorine without any deuterium substitution, we are going to get a singlet peak. This is a single peak. But there are different deuterated analogues of that. What are the different deuterated analogues? I can show you. This is only fluorine. Of course, here proton is being decoupled, and here we have a deuterium in this position. Then fluorine coupled deuterium gives rise to 3-line pattern of equal intensity. I showed you like CDCl3 and the others. When it spin over nuclei coupled to spin off nuclei, you get 3 peaks of equal intensity. Again, the deuterium is not cis here, it is trans to this fluorine. We get 3-line pattern again, and this is deuterium geminal to this fluorine. And of course, there are two deuteriums, both could be one semi-trans, one cis, one geminal, one semi-cis, and one trans, one geminal, one cis. Varieties of possible combinations we can see. And if you carefully look at it, you can understand one thing from this spectrum. Remember, when the deuterium is there in the geminal position, the separation is larger. Then it comes to trans, then comes to cis. What do you understand from that? The J coupling between fluorine and deuterium is larger in the geminal coupling, is for geminal coupling, then trans, then cis. You know, it is a completely a reverse phenomena or a different phenomena compared to what we observe in protons. In protons we saw trans coupling is larger, then cis coupling, then geminal coupling. But here you see geminal coupling with fluorine and deuterium is larger than trans than cis. This is the phenomena. And so 2 bond chemical shift also is larger more for that of the trans 3 bond chemical shift than this one. Similarly, J coupling, J geminal is larger than J trans than J cis. So, not only chemical shift of 2 bonded is larger than trans 3 bonded and cis 3 bond chemical shift. That means 2 bond chemical shift means that is one which is geminal. So, geminal chemical shift is larger than trans chemical shift than cis chemical shift. That is what it is. Similarly, we also got the information about J couplings. With this idea, we will see how we get the pattern. Of course, when 2 deuterium are present, one is trans, other is cis. What is the pattern we get? First, it is going to be a triplet, 3-line pattern of equal intensity, and each of them is split into 3 lines because of our second deuterium. If you come to this pattern, of course, geminal coupling as I said is larger, that is a first one, large 3-line pattern, and each of these lines is split into 3 lines like this, that is another one. Go to the last one, geminal and trans, geminal coupling is large and trans coupling is next one. So, this is like this, each of them will be 3 lines like this. Multiplicity pattern can be very easily assigned, but the only thing is you see the difference in the chemical state positions each of them because of deuterium substitution, whether it is mono substituted, di-deuter substitution, whether it is cis, trans and geminal makes a lot of difference in not only appearance pattern, but also in the chemical state positions. That is what I wanted to tell you. Now, from this we can get JFD coupling, deuterium fluorine coupling. Can we get deuterium proton fluorine coupling from this? Of course, remember I explained to you when I discussed about the magnetical equivalence, HH coupling, deuterate one of the hydrogen atom, HD coupling you get, and we could get using the ratio of the gammas, we can get HH coupling. Exactly here, gamma H and gamma D is is this one. Now, use this value, ratio of the gammas, and then get the measure the FD coupling, convert that into this one, and you are going to get JFH. From measured JFD, you can get JFH. That is what we are going to get. For all the cis, trans and other things, JFH can be measured here. Okay, that is about fluorine. We will continue keep going, otherwise there we will be stuck with only one nuclei for a long time. Let us look at the second nuclei, that is phosphorus NMR. Another friendly nucleus because it is 100% abundance, spin half. Spin half nuclei is always friendly nuclei for us. Let us see 4 different types of molecules. Take an example like this. We see the phosphorus NMR of that. Each of them is coupled to fluorine. First one is PCl3, no fluorine. Chlorine is a quadrupolar spin, generally it will not come, it will not couple, you ignore it, the quadruple coupling is enormously long, it is coupling for that is not seen. PCl3 gives a single peak, fine. PFCl2 gives a doublet, 2 peak. PF2Cl, because 2 fluorine is chemically equivalent, gives a triplet. PF3, see slowly we are removing 1 chlorine and adding 1 chlorine. PF3, 3 fluorines are chemically equivalent, makes this phosphorus a quadret, 4 lines of equal intensity. I am sorry, 4 lines of intensity 1331, it is a quadret. Okay. This is another interesting example. Let us look at the analysis and 31p spectrum of this molecule HPF3 in CdCl3. What are the couplings we can see for fluorine and phosphorus? For phosphorus, there are 2 couplings. One is phosphorus proton coupling, other is fluorine phosphorus coupling. There are 2 types, JHP and JFP. There are 2 couplings. And JHP coupling is quite large generally. That will be a doublet, very large coupling, that will be a doublet. and each line is a doublet. Initially it is going to be a doublet because of JHP coupling, and each line is this thing is going to be a quartet like this. Some of the quartet lines are overlapped. It is going to be a quartet. What are these things? We can now identify very easily. This is JPF coupling. One bond, that is because of not one bond, of course, 3 fluorines are present, is a quartet. Any two adjacent line of the quartet if you take, it will give you PF coupling. And what is the HH coupling here? HP coupling. HP coupling is here. See, this is HP coupling, and subsequent lines you can consider this one. You take this to this line, that is HP coupling. Again, this to this you take, you get HP coupling. Very easily you can get HP couplings. HP couplings are easily obtainable. It is a doublet, and each line of the doublet is a quartet because of this thing. So, this is how you are going to get 2 quartets, 1 quartet for one doublet, one of the doublets of HP, other quartet for other doublet of the HP coupling. So, this is called quartets of doublet. This is a simple molecule. It is only not full spectrum, partial spectrum is shown here, but remember it is proton coupled. It is very explicitly written here. What is the meaning of that? Now there are 2 phosphorus, both are chemically inequivalent. This phosphorus is different, this phosphorus is different. Each of these phosphorus can experience coupling with protons and fluorine. Now my question is, what is this phosphorus? This is a partial spectrum of one of the phosphorus. I mean partial spectrum of the entire 31p spectrum pertaining to only one of the phosphorus. Now this corresponds to which phosphorus? Very interesting to observe. First of all, you please note this phosphorus can couple to this phosphorus also. They are chemically inequivalent. So coupling can be there. One bond PP coupling is there, and then we have 2 bond HP coupling is there. In addition to that, we have 1,2 bond PF coupling is also there. If you come to this phosphorus, 1 bond HP coupling is there, 1 bond PP coupling is there, and 1, 2, 3 bond PF coupling is there. Each of these fluorine can experience different couplings. Looking at the pattern, I would say this corresponds to this phosphorus, because this for this phosphorus to have coupling to this 3 fluorine, 1, 2, 3, 4, 5 bonds away, 4 bonds away, to become a quartet is very weak, it is quite unlikely. That is my first guess. So I would say this is for this phosphorus, because this phosphorus can experience direct 1 bond coupling and 2 bond coupling and also 3 bond coupling, with all the 3 can be present here. So I would say this is this phosphorus, and it is a direct 1 bond PP coupling is quite large, about approximately 195 hertz. It is a doublet. It gives us a doublet. Then what will happen? Each of this line is split into a septet like pattern, because these 2 fluorines are equivalent to CF3 groups. So it is like 6 fluorines coupling to this phosphorus. 2 into Ni plus 1 we will rule apply, 2 into N is equal to 6 into half plus 1. So it is going to be 7 line pattern. It is going to be a septet pattern. This separation is a septet. Each of this is a septet pattern. 1, 2, 3, 4, 5, 6. You can count, there will be 7 such lines. It is a septet, and that coupling separation is 70 hertz. That is also fine. Okay. And interestingly, and each of this septet line is split into a triplet because of this CH2 proton. So this phosphorus experiences 3 couplings. PP coupling is a doublet. Then it is a septet because of 2 CF3 groups, and it is also each line of the septet is a doublet. Triplet because of PH2 group. So this is one septet of triplet for one of the doublet. This is another septet of triplet for another doublet. So the total pattern is doublet of septet of triplets. So this can happen only for this phosphorus. I hope it is clear for you. Let me repeat. For this phosphorus, there is a 1 bond coupling, it is a doublet. which is here, this peak and this peak, center of that, and each of this doublet splits into 7 line pattern, and we have to see 1 2 3 4 1 2 3, they will be overlapped. There will be 7 lines from the center, 3 this side, 3 this side. Similarly, for this 3 septates here, 3 septates here. This septate is coming because of these 2 CF3 groups. That is not all. Each of the septate is split further by PH2 group, that is a triplet. So, it is going to be septet of triplets. So, each doublet is going to be septet of triplets. So, there are 2 such things. Okay. As I said, this is one septet of triplets, this is another septet of triplets. There are 2 such septet of triplets, some of the lines are overlapped here, and total pattern is doublet of septet of triplets. Very easily you can do that. Now, this is the next phosphorus. Obviously, this is the pattern. This is something very interesting. How can we get, this is again some funny pattern here, we will see what it is. Looks like a quartet of some septate or by quintet like that. How do we get that? It is written here, remember JPH2 and JPP is approximately equal to. What is JPP? Here I saw JPP is 195. That means JPH2 and PFP both are around that order. As a consequence, what happens? One will be a doublet and each line of the doublet will be a triplet. Then it can overlap and gives us a quartet. How? Remember when we understood the multiplicity pattern, we discussed this at stretch. Look at this one. This is this phosphorus, triplet of doublet of septate. Why do we get this one? First it is a pH coupling, we call it a triplet. Does not matter. Then each line of the triplet is a doublet because of this, and central lines will overlap and appear like a quartet. And each line of the quartet then is now split here because of 2 CF3s as a septate. So, it is triplet of doublets of septate. Triplet coupling is slightly larger than this one, approximately equal, but this is more little larger. As a consequence, it is, we have to say first triplet coupling is larger as triplet, then each line of the triplet is a doublet, and each line of this doublet is going to be a septate. So, it is triplet of doublet of septate is the pattern for this phosphorus. You understood? A simple molecule. Phosphorus spectrum, if you take, there will be 2 groups, 2 chemical sheets, one for each phosphorus, and the multiplicity pattern is very much different. For one of them it is going to be a different pattern, doublet of triplet of septates, other is different pattern we saw. So, this is how it is. We go to the other molecule, POCA3 twice. How many peaks we expect for this molecule? If I do not tell you how many peaks, if you do not read this, simply you can count the number of peaks. You are going to get 10 lines because all the 9 phosphoric protons are equivalent. So, 2Na plus 1 rule if you apply, 2 into 9 into half plus 1, it is going to be 10 peaks. Are we getting 10 peaks? See here 1, 2, 3, 4, 5, 6, 7, 8. Wait are other peaks, one is here, one is somewhere here, you do not see it, very weak in intensity. It is 10 line pattern. This any of the separation will give you pH coupling, phosphorus and proton coupling. Then what are the small lines which are seen here, which is written star here? Remember, this phosphorus can also have a coupling with carbon in natural abundance, 1.1%. Obviously, that will give satellites, and that is what you are seeing. Phosphorus coupled to carbon is appearing as satellites. Okay. Simple other molecule. Here only one type of proton is there, CH2s, but there are 2 phosphorus, P alpha and B beta. See, this P alpha can couple to all the 6 protons which are equivalent. It will be a 7 line pattern from same TONI plus 1 rule, and for P beta also it can couple to all the 6 chemically equivalent protons, gives rise to 7 line pattern, but the coupling strength is slightly different. This is about close to 9 hertz, this is close to 2.5 hertz. And very easily You can say why it is 7 lane pattern, because all the CH2 protons are equivalent. 2 into 6 into half plus 1, you get 7 lane pattern. It is a septate pattern, like what we saw in the previous example for CF3, which we got septate. Exactly, we are getting 7 lane pattern septate, and for 2 phosphorus 2 septates are there, and couplings are different, so separations are different. Very easily you can even assign this is P beta, because this is large coupling is there, separation is larger, this is P alpha. So from the coupling, from the separation, you can make the assignment of each of these phosphorus. Okay. So go to this molecule. This is something very interesting, which I wanted to discuss little bit more. This is a molecule where we have phosphorus and lithium is also present. Remember, lithium has 2 isotopes, lithium 6 and lithium 7. Lithium 7 spin is 3/2, lithium 6 is spin 1. We already discussed about boron 3/2 and boron 3. Here spin is 1, not 3, that is the difference. Boron lithium 7 spin high when it is coupled to phosphorus. What is the type of spectrum you are going to get? Remember, its proton completely decoupled. It does not couple to proton. Only we are looking at lithium phosphorus coupling. Carbon is very weak natural abundance, forget it. You will see acetylates. So when you are looking at phosphorus lithium coupling, lithium 7 has abundance 92%, quite large. Lithium 6 abundance is 7.4%, appear like a satellite. One appears like abundant spin coupling, other appears like a satellite peak. Which is which? We have to understand. We will see this. And there are 2 possibilities you can think of. One possibility is both the lithium could be 7. That possibility is there. When both the lithium is 7, what will happen? One lithium splits phosphorus into 4 lanes of equal intensity. That is what we saw for 3/2 spin. Because its spin is 3/2, we have 4 lines of equal intensity. 111 intensity, I took it. What does second lithium do? It will split each of these lines into again 4 lines. From the center I wrote 4 lines. Now add up the intensity. It is 1, 2, 3, 4, 3 to 1. And that is the pattern you should get. When both the lithium are lithium 7, which has spin 3/2, when it is coupled to phosphorus, you get 7 line pattern of intensity 1, 2, 3, 4, 3 to 1. That is exactly what we got here. See here, 7, 1, 2, 3, 4, 3 to 1. This is 7 line pattern coming because of coupling of both the lithiums to phosphorus. When both the lithiums are in lithium 7 spin state, both are lithium 7, then you get this one. Then what about these small lines? So we could explain strong intensity, big peaks, 7 lines, 1, 2, 3, 4, 1, 4, 3, 1, 2, 3, 4, 3 to 1 lines intensity pattern we explain when phosphorus is coupled to both the lithium in 3/2 state. What about the other one? Now we will try to understand this one. This is very easy. Of course, what is the intensity pattern? When both are lithium, I said 92% abundant, both 92% abundance, if you multiply 85% intensity. So those intensities are 85% and the remaining has to be 15%. Okay. And you measure the separation there, large 7 line pattern. Any adjacent peak if you measure, you get the coupling between lithium and phosphorus. Lithium 7 and phosphorus to be precise. That is 45 Hertz. It has been measured. You understood? The phosphorus now it is coupled to both the lithiums. Both lithiums could be, one could be lithium 7, both other could be lithium 6, and both could be lithium 6 also. One lithium or the other lithium 6 also possible. Both lithium 6 is abundance is very small. We will see that one now. In both, one is lithium 7, other is lithium 6. What is the probability you can think of? When one is lithium 7, that splits into 4 line patterns, equal intensity, that we have been discussing because spin 3/2. Now what is happening? It is also coupled to lithium 6. What is its spin? Its spin is 1. So, when spin is 1, each line is split into 3 lines of equal intensity. That is what we have been explaining, discussing in CDCl3, CFC3, everything we discussed. CDCl3, we just showed that deuterium is coupled to spin off, it will be 3 lines of equal intensity. So, it will be 3 lines, this will be 3 lines, this will be 3 lines, this will be 3 lines. And then this coupling is only 16.7 hertz. As a consequence, what happens? There will be 12 lines of equal intensity, most of them do not overlap, but this separation is 45 hertz and this is only from here 16 hertz. So, as a consequence, these lines are very well separated, the overlap is not there, because you see one is here, other is here, this is 45 hertz, and from here they will have 3 lines of 16 hertz. So, there is no question of crossover or overlap with the other peaks. All 12 lines should be visible. See here, see this is, if you see that this is one, when both lithium are 7. Now we start looking at this peak, start looking at this one. When one is lithium is 7, other is 6, first it will be 4 line pattern and each line is split into 3 like this, you see. But unfortunately some are overlapped and you do not see it. See, of course I have highlighted this in green, but you see 3 peaks here, 3. If you remove this, you will be very clearly see, you can see these 3 peaks here, 3 peaks here, 3 here, 3 here. So, all 12 peaks can be easily assigned, and this the adjacent separation of this gives you lithium 6 to lithium phosphorus coupling. This is lithium 7 to phosphorus coupling. So, we understand this is a simple molecule. Spectrum appears very simple, but you need to use the isotopic abundance, spins of different isotopes and get the multiplicity pattern to make the assignment. So, we could easily assign both the peaks coming because of coupling to lithium 6 and lithium 7 with phosphorus. So, this is done very easily, we could do that. Next we will go to another simple molecule, phosphorus, very simple molecule. Can you imagine a simple molecule, this phosphorus I am looking at will give enormously complex spectrum? Hard to believe, right? Looking at simple molecule. And interestingly, you should also see nitrogen 15 is labeled. What do you mean by labeled? We have made it 100%. Otherwise, abundance is 0.37. If it is natural abundance, we do not bother about it. It is a satellite peak, we do not even see it with such a small intensity, 0.37% abundance, we generally ignore it. Unless you are specifically interested to see the satellites, enhance the intensity and acquire for a long time data, you have to acquire for several hours to see that. But it is labeled. So, you should treat it like an abundant spin like proton and fluorine and phosphorus. So, nitrogen is also like abundant spin now because of labeling. So, this phosphorus can experience 4 different couplings. One, it can experience coupling with proton, it can experience coupling with fluorine, it can experience coupling with this nitrogen, it can also experience coupling with this proton. 4 different types of couplings it can experience. The pattern is very difficult to understand, and such a simple molecule, it can experience 4 different couplings, one heteronuclear, another heteronuclear, another heteronuclear and then another heteronuclear. So, 3 different types of heteronuclear couplings are there for this phosphorus. Very interesting example I am giving you. Please understand this one very carefully. Now, we are looking at the phosphorus NMR. This phosphorus can have one heteronuclear coupling, another heteronuclear coupling, another heteronuclear coupling here because of nitrogen labeling, and also another heteronuclear coupling like this. 4 different heteronuclear couplings. And I have given you the values of this approximately because analysis has been done. I do not want to measure and keep on spending time to analyze the spectrum for you. 1 bond pH coupling, this is 836 hertz, very large, very large. And 1 bond PF coupling is also large. And 1 bond nitrogen phosphorus coupling, that is also quite large, 50 hertz. And 1 bond, I am sorry, not 1 bond, 2 bond pH coupling, H2 to this H2 group can couple to phosphorus. That is also quite reasonably large, about 12 hertz. So, all the 4 couplings are quite reasonable, especially one bond coupling is very large, and this one bond PF coupling is very large, and one bond PN coupling is also very large. Some have a negative sign, do not worry about that, that we will see later. And this is the typical spectrum for the phosphorus. Very interesting. You can see this in the book. I have taken this from the book of Inorganic Molecular Chemistry. Fantastic book. When you read that, I saw this very interesting example I have taken from them. I thank the author for, I was able to take the spectrum from that book. So, very interesting example. Look at this. How do we get this Multiplicity pattern? Can we explain this? First, let us say this is the chemical sheet of phosphorus. That is well known. It will be always at the center of the multiplicity. Only a single phosphorus, center of this multiplicity is the chemical shift. And this is the large separation, is a doublet, 836 hertz. I will call it as JPH coupling. Fine. And from this, each of them is coupled to fluorine, and it will be a doublet. Please understand, this is a one doublet. I will say one is here, one is here. This is pH coupling, and each of the doublet is further split by fluorine into doublet, and this is a one doublet. Oh no, I am sorry, triplet, because there are 2 fluorines, triplet. So, 1 to 1 triplet is there. So, 1 intensity 2 and 1 intensity is one triplet. This separation gives you FP coupling. Okay, this is another triplet. Another triplet is because you look at this one triplet, from this 1, 2 and 1, another triplet. You understood the thing? Let me repeat, this is one doublet because of phosphorus proton coupling, and from the center of this doublet there is a triplet pattern 1 to 1 intensity 1, 2 and 1. This central peak anyway will not change its position, it is there only. This is because of P coupling with 2 equivalent fluorines. Similarly, this also is split into a triplet, and this coupling is again 619. So, we got doublet of triplets. Fine. Now, we will expand one of them here. When it is expanded one of them, there is also PN coupling. This coupling, there are 2 nitrogens which are equivalent. So, that will split again into a triplet similar to this fluorine. 2 nitrogens are splitting this, each of this line into, we got doublet of triplets, right. First there was a doublet and each line is a triplet. So, there are 6 lines here, doublet of triplet, and each of these 6 lines here you see 1, 2, 3, 4, 5, 6 lines. Each of these 6 lines is split into a triplet because of PN coupling. Okay, that is 1, 3, 1, 1 to 1 triplet. Interestingly, this also coupled to 2 H2s, 2 equivalent protons. There are 4 protons, 2 equivalent protons, 2 each. Then each of them is split into a quintet pattern like this. See, 2 pH coupling is like this is one quintet, another quintet. There are 3 such things. Very interesting. Let me repeat it for you to understand how such a simple molecule can give rise to a spectrum. This is center of the chemical sheet of phosphorus. It will doublet because of pH coupling. Each line of the doublet is split into a triplet because of PF2, and each line of this triplet of doublet is split into another triplet because of PN coupling, and each line of the triplet is further split into quintet because of 2 groups of H2s. So, 4 protons, and that is a quintet. So, this is what it is. So, what is the total pattern? Total pattern is doublet of triplets of triplets of quintets. So, doublet of triplets of quintet or pentet, whatever we call. So, totally how many peaks we get? 90 peaks. It is a simple molecule. One phosphorus spectrum if you take, without doing any decoupling, all of them are coupled, you are going to get 90 peaks. Very complex spectrum, still we can interpret the multiplicity pattern. So, I think time is getting up, I am going to stop it here. Today we discuss a lot about fluorine NMR, phosphorus NMR, lots of examples I took. I could analyze the fluorine spectra of several molecules. I showed you isotopic effect, especially with chlorine substitution, CFCl3, deuterium substitution of vinyl fluoride molecule with this deuterium single monodeuter substitution, dideutero substitution in the ortho position, in the cis position, geminal position or trans position, and how the coupling varies. And I showed you geminal coupling of FD is larger than cis than trans. So, this part we also observed that, and we measured the chemical shift also, how the chemical shifts are changing, the isotopic effect very easily we could see. And I took the example of another molecule PCl, how different fluorines coupled to different types of fluorine present gave rise to a septate. From the septate separation I could identify the phosphorus. Now, in another example of a molecule like this, we have plenty of things. Phosphorus coupled to proton, 2 equivalent fluorines, 2 equivalent nitrogens and 4 equivalent protons, and we got 19 lines. And the pattern was doublet of triplet of quintets. Fantastic. And if you have the idea of how the pattern comes, we can make the assignment. So, this is what I wanted to explain to you. I will stop here. Already I take a lot of time today. We will continue with the discussions in the subsequent classes, for not only one or two example of phosphorus and some other heteronuclear. Thank you very much.